Welcome back, everyone. We're in sound today, chapter 26, and I like sound. I like how it works. So let's look at some of these things today. Two major classes of waves are longitudinal, transverse. So a longitudinal wave is where you get compressions and rarefactions and compressions and rarefactions, and eventually it starts wiggling your eardrum. Your eardrum will wiggle because this will make it vibrate, and then the next one will make it vibrate, and then there's a wavelength in between. Then the bones in your ear are connected to this tympanic membrane or this eardrum, and it'll basically slosh some stuff on the inside of your ear that's connected to your nerves, and you perceive it as sound. Pretty cool. So these are longitudinal waves, like sound waves. Transverse waves are like water waves, where you're actually going to have a wave pattern going in some direction, but these guys are just going to go up and down. So the molecules, say in the lake, are just going to go up and down, but the energy can transfer left or right. So sound waves are longitudinal waves. The frequency of sound signal refers to how frequently the vibrations occur. A high frequency sound is heard at high what? So we call high sounds high pitches and low sounds low pitches. The frequency, a high frequency sound is heard as a high pitch. Wavelength, remember, is backwards of frequency. So you would have a very short wavelength for a very high frequency sound. This is what I was talking about in lab the other day. If these were the nodes, remember that we had kind of things in the string, if you remember the string, where you had these kind of places. Actually, it's backwards. It's here, and then rarefaction here and rarefaction. Remember, these are the harmonics that we talked about when we saw that in the string. So the sketch shows a snapshot of the compressions. So here's the compressions and rarefactions. So this would be one wavelength of the tube in an air as the sound moves towards the right. The dots represent, I guess, the air molecules. With a ruler, the wavelength of the sound is measured to, don't know. Let me get a ruler. So the wavelength would be, let's do it in centimeters, 1 3/4, so 1.75 centimeters. You can see how that it's repeating each time, and that would be one wavelength from crest to crest or from compression to compression. Compared to the wavelengths of high-pitched sounds, the wavelength of low-pitched sounds are what? Okay, so if you have very high pitches, the wavelengths are going to be very short together. If you have very low pitches, the wavelengths are going to be very long. So they're going to be opposite of each other. If you remember, wavelength times frequency is the sound. So as one goes up, the other's coming down. They're inverted. Suppose you set your watch by the sound of the noon whistle from a factory 3 miles away. Compared to the correct time, your watch would be what? Well, remember, it takes 340 meters per second for sound to travel, and if you've got 3 kilometers, you're going to be several seconds behind because it took that time from the time the whistle tooted to the time you heard it. It's going to take some seconds to get there. So how many seconds will that be? All right, so if you have 3 kilometers, and we know that in 1 kilometer there is 1,000 meters, and there's 340 meters per second. How many seconds is that going to be? Okay, so on the calculator, I'm a mess today. So you're going to have 3,000 divided by 340, that's 9. 9 seconds, 9 seconds delay. All right. Sounds travel fastest. Okay. Sounds travel fastest. What you're going to see is the more dense the material, where the molecules are very, very close together, the energy will go from one to another very fast. When it's a very loose material, okay, like air or something like that, the energy is losing. There's actually losing speed as it's going through this nothing. Okay, as one molecule is popping into another very, very close, you're going to get faster speeds. So you could, like elephants can feel or hear, if you want to think of it as hear, way farther with their feet than they can with their ears. Even though they have huge ears, their feet are so big that the vibrations in the ground are they travel very far and very fast, and so they can actually pick it up with their feet. So solids will go much faster than in a liquid or in a gas. If a child's natural frequency, we talked about natural frequency of any object, so this is a swing, has natural frequency. If the child's natural frequency of swinging is once each 4 seconds, for a maximum amplitude, the man should push the rate how? Okay. Remember, in our lab, if we could push that pendulum at its natural frequency, we got it to oscillate at a higher amplitude than before. So if its natural frequency is 4 and he wants it to go farther, he wants to push it at 4 seconds. So whatever that is, you can kind of see how fast you're going to do to make it go faster or make it go farther. If the man in question 7 pushes in the same direction twice as often, okay, what's going to happen? Okay, if he pushes twice as often, so he pushes, okay, she comes out like this and then comes back, then he pushes again. If he pushes twice as often, then like she won't be there. Like she'll be over here when he pushes, and I guess he would be pushing. She would be moving backwards and he would be moving forwards. So he really shouldn't do that. So he has to wait for her to get back before he pushes again. That's like the first rule of swinging. Okay, number 9. The frequency of a tuning fork is 440 Hertz. That happens to be an A. I know that. I don't know why. It will not be forced into vibration by a sound of. Okay, so what you're going to see, this is called sympathetic. If I can make a sound at 440 Hertz, this will start vibrating if it's its natural frequency. Okay, if I can half that, I can send it going a little bit. But twice that is too far and it won't work. So the answer would be 880 Hertz. It won't force a vibration. Beats, we'll talk about beats in lab. Beats are the result of alternate cancellation and reinforcement of two sound waves. So what you're going to say, let's say if you have a tone that's 440 Hertz. Okay, let's say you have one violin player playing 440 Hertz and another violin player playing 337 Hertz. What will happen is as this one is going here and this one is going here, you're going to get some cancels, okay? And you're going to get some increases. So when they overlap, they will either positively reinforce. Remember we did that in a lab before to where you have two that overlap and they actually become twice as loud. And sometimes they will cancel like this and become just a straight line and nothing happens. And those, what you end up with is kind of like dat, 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 dat. You can hear them. They're called beats. And it's because they're different, slightly different frequencies. They have to be really almost in tune in order to do that. The closer they are in tune, but they're still out of tune, the closer they are, the faster the beats you'll hear. Two notes with frequency of 66 and 70, so that's what we're talking about, very close, are sounded together. the resulting beat frequency, okay, is the difference between them. So you've got 66 to 70, so you have 70 hertz, 66 hertz. The resulting beats are going to be the difference between them, will be in 4 hertz. Okay, last question. The accepted value for the speed of sound in air is 332 meters per second at 0. The speed of sound in air increases at 0.6 meters per second for each Celsius degree above 0. Compute the speed of sound at the temperature of the room now. So if we are at 25 degrees Celsius, which is room temperature, then that's 25 times 0.6, and then, I don't have my calculator, 25 times 0.6 added to 0. You see, so that would be, I don't know, like 14 degrees or something like that. So it would be 332, 336, so 346 meters per second, something like that. Okay, thanks.